Hello, this video of a wiring diagram for a small 12-volt system is aimed for beginners who want to understand a bit about electrics, the whys and hows behind their system, and not just how to wire it. I've tried to do it simple, but also make sure I go into a bit of detail about products, tips and tricks, safety things to think about, like wire size, fuse size and where to place them, and just how to wire the whole system. If you'd rather watch a shorter version without all the information and the whys and my reasonings behind my choices, there'll be another video for that, just to quickly show you what the diagram would look like. Anyway, let's begin. First we need a solar panel. If you can afford it, I'd recommend getting the monocrystalline solar panel instead of the polycrystalline one, as they last a bit longer and are more efficient. In my example, I'll be using a 120 watt solar panel, 22 volts open circuit, although it's more like 18 to 19 volts otherwise. We'll get more into open circuit later, but for now, just see it as an 18 volt solar panel because that's what it is. Now it doesn't have to be specifically an 18 volt solar panel. I've seen 17, 18, 20, 36. As long as it's quite a bit higher than 12 volts, you'll be fine, because you need more than 12 volts to charge 12 volts. I'd recommend using a 17 to 18 volt or higher solar panel. A 120 watt 18 volt solar panel will charge at perfect conditions about 6.7 amps. 120 divided by 18 is 6.7-ish. But during the night, or should it be very cloudy, you won't be getting nearly as much, if any sun, which means no power or no electricity. Furthermore, even if it's super sunny and you do get those 6.7 amps, that's all you're going to get, meaning you can't use appliances that draw more than 6.7 amps, which is not very much. And these 6.7 amps aren't very stable either. They can fluctuate, for example when moving clouds block the sun a bit. Also, you don't want to push 18 volts into your 12 volt appliances. They're not built for that. And 18 volts is not sufficient enough for 24 volt appliances. To combat this, we use batteries. This means that you can charge a battery for several hours with 6.7 amps. And after several hours of charging, you've got quite a lot of energy to use, meaning you can, use an appliance that needs 20 or 30, 40, 50 amps to operate. A silly metaphor, but imagine being very thirsty and needing to gulp down lots of water at once. Sure, rain supplies water, but you can't really drink it fast enough. It'd be a lot easier if you had a barrel or a bucket or something that could collect the water, and then you drink the water from there. Moving on. There are two types of batteries people usually like to use. There are several more, but these are the ones people opt for campers and, these sort of installations. AGM and lithium. Now, in the past, people have been very wary about having lithium batteries in their vehicles because they've been afraid of the batteries self-igniting, which of course is not so good, or I should say is very, very bad. However, these other lithium batteries that have gained popularity lately, lithium iron phosphate batteries or LiFePO4 batteries, are different and they don't really self-ignite. They need a lot higher temperatures inside for that to happen, and as far as I've understood it, it's almost impossible for that to happen unless you add flames or external heat. But then again, any battery would kind of burn up if you were to throw it inside a fire or use a flamethrower on it, so just don't do that. So, safety's gone up a lot, but that's not all. Prices have also come down quite a lot. If you compare battery to battery now, the same amp hours, they're almost at the same price, AGM and lithium iron phosphate. In the past, the difference was quite big. However, these days, even with the AGM being slightly cheaper, I would still opt for the lithium iron phosphate battery, as you get more bang for your buck, or euro or pounds or whatever you pay in, because it's got way more life cycles. You can charge it and discharge it way more times, like thousands instead of just hundreds. Furthermore, you can also discharge the lithium iron phosphate batteries a lot lower, down to 0 to 20%, and they'll still be fine. This means you get almost 100% of the battery's capacity, but if you've got an AGM battery, you might not want to discharge it to much more than down to 50% if you want it to last a long time. Of course, doing it down to 20% once might not kill it, but still. This kind of means that you get twice the amp hours out of a lithium iron phosphate battery compared to an AGM battery, if they are both 100 amp hours. Because of these factors, even if you choose to get the more expensive LiFePO4 batteries or lithium iron phosphate batteries, you're still going to get more bang for your buck, even if they are twice or thrice as expensive as AGM batteries on paper. But if you buy the cheap lithium iron phosphate batteries, some of them are good, some are not as good, then they're the same price as AGM, even on paper. By the way, I made a silly mistake earlier and took 120 watts divided by 22 volts and got 5.5 amps, and accidentally put that up in the video most of the way. It's supposed to be 18 volts and 6.7 amps, but it's just too much work to change every single picture, so just bear with it that from now on it will say 22 and 5.5, but it's wrong. Now, moving on. To charge this 12-volt battery, we need some wires going from the solar panel to the battery. The solar panel will always come with 2 wires attached to it, one for positive and one for negative. These wires are usually not longer than a meter though, and the ends look like this. So there's a female and a male. So I'm just going to add them to the diagram. There we go. I will discuss wire size and fuse size a bit later on, but for now, just ignore it. Because these wires that are attached to the solar panel aren't much longer than like a meter, usually, they won't reach all the way into the van and where they need to go. So, what I like to do is buy a packet of solar cables, although they are wires really. It could be a 3 meter packet, a 5 meter, 10 meter, pick whatever you need for yours. Some will come with these MC4 connectors on both ends of the cable or wire. Others will only have it on one end. I prefer getting the ones that only have it on one end, like the one on the right, because that means that the side that is MC4 connected can go directly to the solar panel, and then the bare end, or the one without, will be able to fit through an entry gland like this. This will ensure it stays watertight. You can add your own connectors and crimp them on, but that requires certain tools. Okay, so let's add our entry gland plus some wires. It goes on the roof, and you seal it off with mastic all around, like underneath the entry gland. Some UV resistant, weatherproof mastic so it doesn't start leaking within a few years. The wires on the inside of the van, they don't have to go to a switch if you don't want to on such a small installation, but I like to do it that way. It's so that you can switch things off if you're going to do some maintenance, but one solar panel with 22 volts will probably not even be felt, and it certainly won't harm you. But if you don't want the power on anyway, because maybe you got sensitive components that can't handle it, or you simply don't want to risk a spark or whatever, you can always cover the solar panel with a piece of cardboard on the outside. But in this diagram, I am going to use a switch because I think they're good, and also for future proofing. It means you can add many more solar panels, increasing the voltage, and don't have to worry about covering them all with cardboard every single time you want to make a change in your system. But don't just use any old switch laying around the house. You want a specific switch, a DC breaker that can handle the right amps and voltage. Without getting into too much detail, DC arcs, electrical arcs, are a lot harder to extinguish than AC arcs, so get a DC breaker. Just search solar DC breaker and you'll probably find lots of them, and read the specs. Okay, perfect, so now we've installed the breaker, let's move on to the next part. Tempting as it might be, we can't just attach these wires straight to the battery because we'll fry it. This solar panel is 22 volts, the battery is only 12 or 13ish, but it will fry the battery, which we don't want. So we need a unit that can monitor the voltage and the current from the solar panel and then convert it or transform it, kind of step it down to a suitable voltage that the battery can handle. A regulator of a sort. These are, for example, such objects, MPPT solar charge controllers. There are other versions as well that look like this. They don't have screens, but you might connect them to your phone via Bluetooth, or perhaps you might have a separate little display with a cable going to the charge controller. Again, without going into too much detail, because this was supposed to be a simple video, there is the MPPT solar charge controller, more efficient, use this one. There's also the PWM charge controller, which is a bit cheaper, but I wouldn't recommend it really. Okay, so let's install an MPPT charge controller here. But fair warning, always wire the battery to the solar charge controller before wiring the solar panel to the charge controller. The solar charge controller needs to know what type of battery or voltage the system is using, so then it can adjust it before the actual charging takes place. Now let's talk about some important specs on the charge controller. For example, the one I'm using works for 12-volt systems and 24-volt systems. But let's focus on the 12-volt system part because that's what our system in this diagram is. We can have a solar panel or solar panels with a total wattage of 260. That's fine because our solar panel is only 120, so within the limits. I'm not going to get too into solar VMP and max solar VOC, but know that max solar VOC means max voltage open circuit. That is to say, the solar panel's voltage when you haven't connected it to anything, when it's still open, if you were to measure directly on both wires. And since our solar panel is at 22 volts open circuit, and when it's not open circuit, when it's connected, it might be something like 18 to 20, I can't remember exactly, but as you can see, it's well within the limits of this solar charge controller, because the max solar VOC, or voltage open circuit here, is 100 volts. Okay, so this is how things might go down with our solar panel. So 120 watts and 22 volts open circuit, although it will be more like 18 volts under load. That is to say when it's connected. So 120 watts divided by 18 volts equals roughly 6.7 amps in the wires flowing to the PV terminals, which are the solar panel terminals. Once the battery's wires have been connected to the MPPT solar charge controller as well, which should be done first of course, but once it's all connected, the charge controller will sense and realize how much the battery needs charging and adjust the current and the voltage accordingly. The 120 watts will remain the same. Energy never disappears, it just converts and transforms. So if the MPPT solar charge controller converts or steps down the voltage from the solar panel to a more suitable voltage for the battery to charge, say 14.4 volts, the amperage or current will go up. Of course, what you see on the screen, the equation, is just a theoretical number in the perfect world. Things aren't perfect and 100% efficient. There will be losses in heat, for example. But I wanted to explain more or less how it worked because in big installations it matters when it comes to sizing your wires. And also it's just nice to understand your system. Speaking of sizing wires, let's do that. Most solar panels will come with wires as thick as 4 to 6 square millimeters, which might sound more than needed, but is really good for future-proofing. They come this way because you might want to add multiple solar panels in parallel, which combines the amperage. So I'm going to use the same size wire from the solar panel to the charge controller. Besides, most UV-resistant standard solar wire or solar cable come in that size already. Now, as I've mentioned, when it comes to actually installing it in real life, you wire the battery to the charge controller before the panels. Of course, the battery's wires go to the BAT terminals. Positive to positive, which is the plus, negative to negative, which is the minus, or red, which is positive, black, which is negative. PV stands for photovoltaic, which is just light being turned into electricity. That's, of course, the solar panels. I know it looks a bit funny, as if I've wired the solar panels wires to the BAT terminal, but that's just because the blue MPPT charge controller I've got here is a bit different. The one above is what I've actually got, and there you see it says PV to the left and BAT in the middle instead. It just varies from charger to charger. We're going to talk about the load terminals you see on the right towards the end of the video, but for now, just know that they're not the greatest and put it out of mind. Sorry, just can't remind you enough about this. With a small installation, you can just wire everything to the battery. That is to say, the MPPT solar charge controller to the battery and all the appliances to the battery. Never ever the solar panels directly to the battery, of course. But anyway, as I was saying, you can wire everything to the battery with a small installation. And since we've got a small installation here, I'm going to do just that, as well as show you another way of doing it, so that looks maybe a bit neater. But that's for later. I just want to show you something first. Another way of doing things if you've got a bigger system, or if you just want it anyway. You can use different types of bus bars, we call them. If you are a fancy snob, I mean if you have a lot of money and don't mind splashing out a bit, there are really good ones that look something like this. Victron's generally a really good brand, and people like them, except they're a bit expensive, but they're good. Victron's Lynx distributor, as this one is called, is more than just a bus bar where you connect all your appliances and your battery, or batteries. It's got slots for fuses and also some smart features. It's got this circuit board behind it with lights that indicate when fuses have gone, for example. I don't pretend to be an expert with this particular one because I tend to go for cheaper options, but I thought I'd mention it. Then there are these. These are regular bus bars. Some come with covers, others without. But you basically connect everything to these. Your battery has two main terminals. The wires going from the battery then go to the bus bars. The MPPT solar charge controller has two BAT terminals. And the wires connected to these BAT terminals go then to the bus bars. And all your appliances also go to the bus bars. Of course, with fuses in between. Okay, now let's continue with the diagram. Now, you're going to want to fuse the battery before anything else. When I say fuse the battery, I actually mean fuse the wire running from the battery to wherever it's going to go. Because the fuse's job is to protect the wire, be the weakest link in the system in case of a short circuit, meaning if the black and red wire touch each other, or just overcurrent for some reason. Say you try to use more power than the wire can handle. You don't want the wire to get so hot it melts the insulation, because that will cause a fire. Instead, you have the fuse melt, of course in a controlled way so that it doesn't catch fire, to its surroundings, and then that will cut the power off. And you want the fuse to be as close to the battery terminal as possible. There are many different types of fuses, like the A&L fuse, or the mega fuse. These are great for like bus bars, but you can install them anywhere you see fit, as long as there's like a stud, or a bolt, or something you can, well, put the ring through, if that makes any sense. There are also ones that are specifically designed for battery terminals. They look like this. The last time I checked, if you want a well-known good brand like Blue Sea, it could cost as much as $40 to $50. They might be cheaper in the future or during different periods of time, but last time I checked, that's what they cost. The random crap brands might be really tempting to buy because of their price, but don't get them if you can help it, because they might blow too early, meaning it will just be a hassle, you have to change them constantly and that costs more money than the good brand in the long run. Or they might not blow when they're supposed to blow, and that's just dangerous. Then we have the resettable DC circuit breakers. The benefit with these is that when they trip, you only have to reset them. You don't have to buy a new fuse. The downside is that they can be quite expensive if you want good quality, something that will last and work the way it should work. I'm not saying all cheap versions will fail or not work, but there have been several cases of them not tripping when they should, or getting very hot. There are many more fuses out there that we could discuss and use, but that will take forever, so let's just move on. I am going to use the A&L fuse in this diagram because I've used them several times in reality and I think they're great. Of course, if you buy the cheapest ones, maybe not, but then again, that's the case with anything. With these fuses and fuse cases, you need these. They're called lugs, or wire lugs, and you crimp them on to the end of the wires, like this. You don't have to get the most fanciest expensive ones, but you don't want to get the cheapest ones either, because then you risk not getting copper or tinned copper. You risk buying like 1% copper with aluminium being the rest, or maybe no copper at all and some other random metal, and then they market it as copper anyway. Some places do, not all. I've done that mistake once and bought crap. I sent it back. You don't want to risk getting hot spots just because you tried to push through the current it promised it could handle. So make sure to get the copper ones, or if you are worried about corrosion, the tinned copper ones. Here's a rhyme to help you out. If it feels too light, then it's probably not right. Copper is quite a heavy metal. To crimp these lugs onto the wires, you'll need a special tool. There are several options out there, and they're usually not that expensive. Okay, now let's fuse the MPPT solar charge controller's battery wires. And like I said before, first I'm going to show you how to wire it directly to the battery with a fuse, and then later show you an alternative way that I think might be a bit better in certain circumstances or for some systems. Both of these examples will be cheap ways of doing it without the expensive bus bars. For the first example, I would use an inline fuse, like this. And of course, there are many different types of inline fuses, but we're not going to talk about them because it will make this video extremely long. So let's just go with this one. They use blade fuses, also known as car fuses. I think they're quite good, but just don't get the absolute cheapest, nastiest stuff because that's rarely good. So you just pop them in like that, This particular one is 15 amps, and that's perfect for our system because, if you remember, 8.3 amps roughly would be running through this wire, the one I just fused, during normal, or I should say optimal, sunshine hours. And we want something that can handle that. Sure, 10 amps would be fine as well, but I'm going to use a 15 amp fuse because, one, the wire is like 4 to 6 square millimeters, which means that 15 amps is definitely fine for that as well, and there's no real price difference between the fuses. Also, those 8.3 amps might not be 8.3 constantly, they might fluctuate down and also up if the solar charging controller isn't perfect, because products don't always charge exactly what they say they're going to charge, and fuses don't always blow exactly when they say they're going to blow. So I want that margin, especially if it's something that's going to be, charging or running consistently every day, many hours. And it's not like the 15 amp fuse is compromising the safety either, because it will still blow as it should during a short circuit, because then the current will be really high. Before we continue with the diagram, let's just talk about fuse placements, like why I put them so close to the battery and why the solar panel has no fuse. So to demonstrate this, let's just complete the circuit by wiring the negative from the MPPT solar charger controller to the battery's negative terminal. There, perfect. Now say that we get a short circuit because maybe a mouse bites away at the insulation so that the copper touches the copper of the other wire, or maybe vibrations from the van causes both wires to rub against something sharp which damages the insulation, and eventually you get a short circuit that way. Or maybe the wires were just really old and the insulation really crap or damaged by the sun or whatever, and therefore the wire insulation just crumbles and boom, short circuit again. So what happens here is that a shortcut or short circuit opens up, and instead of the current flowing through the device, which has some resistance, it takes the path of least resistance. So most of, if not all, flows right from the negative to the positive. The electrons flow from negative to positive, even if middle school likes to sometimes say that it's from positive to negative. Electricians and people who have studied electrics, or physicians, they all know that it's from negative to positive. It doesn't really matter, the battery system will work the same, whichever you choose to say. Now, I don't know if you've ever seen what happens when the two terminals on a battery, like a car battery for example, touch each other. This is what happens. But it can also look a lot worse, depending on how big a battery bank is. If you've got a very large bank where a lot of current can flow, the voltage is higher, and the connection points are better or have more surface area, then obviously more amps will be able to flow. So even a small 12-volt system can be dangerous, but that would be because of the heat, the potential fire if you do things incorrectly. You're not at risk of getting electrocuted, however, because the voltage is simply too small to overcome your own skin's resistance. It can't penetrate you, so to speak. So anyway, going back to our simulated short circuit here, it's the same thing as if both battery terminals were to touch each other, except it's happening right where the lightning bolt is. These kind of batteries can deliver a lot of currents, especially during a short circuit. They are supposed to disconnect because this particular one has a battery management system, or BMS, but never mind that. It's always good to have a fuse in case of a short circuit anyway. So what happens is when it shorts out, you get a large, like many hundreds of amps that try to push through that small little 4 to 6 millimeter wire. But that wire is not designed to handle so many amps. Not hundreds, it could easily burn up. Or, first of all, the copper would get really hot because there are just too many electrons trying to flow at the same time through a wire that can't handle that load. So then it would get hot and the insulation would melt or catch fire, which would then perhaps catch fire to other things. And the fuse's job is to be the weakest link and melt before the wire gets hot and starts melting or burning things. So if we have the fuse really close to the battery terminal, and then a short circuit occurs, and so the fuse melts, then the power will be shut off. Current won't be able to flow past the fuse. This is why we want the fuse close to the battery terminal, because if the fuse was on the other side instead, so to the left side of the lightning bolt I've drawn here, firstly, the fuse might not even blow. But even if it blew, because the wire would still be hot, and so the heat might still travel and reach the fuse and cause it to melt, that would still not stop the current from flowing through the short circuit, because in that case the fuse would be on the left side of the lightning bolt, which means that electrons could still flow from the negative terminal through the short circuit and straight to the positive without the issue of trying to get past a blown or melted fuse. So again, the closer the fuse is to the battery terminal, the safer it is and the more wire it will protect. Now let's talk about why I did not fuse the solar panel. Let me just change the picture back to the other one. There. Now don't worry, I'm going to add the negative wire and the text about the fuses back in just a bit. Anyway, if we focus on the solar panel for a bit, we can see that ours, for example, produces roughly 5.5 amps. In real life, behind your solar panel or in the datasheet, it will say how many amps yours produces during normal operation and also how many flow through during a short circuit between the two wires running from the solar panel. The difference is very small. It might be something like 6.7 amps during normal operation and 7.5 amps during a short circuit. And this is because the solar panel can't produce more power, even if it's shorting out or there's a short circuit. The panel size is just too small. The surface area can't collect or gather enough sunlight to produce hundreds of amps with that particular voltage. And since the wires that come attached to the solar panels usually have 4 to 6 square millimeter wires, they can definitely handle the short circuit current of, say, 7 to 8 amps. As a matter of fact, it would be stupid to try to fuse it because we'd need a fuse size larger than 6.7 amps, because otherwise it would blow constantly during normal operation, but also a fuse that is rated for currents lower than 7.5 amps, or whatever the short circuit current might be. If we were to use a fuse rated for currents larger than the short circuit currents, in this particular case with this solar panel, like a 10 amp fuse, it would never blow even during a short circuit, which would defeat the whole purpose of the fuse in general. The time you might want to have fuses with solar panels would be if you've got lots of solar panels and they're wired in parallel. This is because wiring them in parallel increases the current, or the amperage, which could, during a short circuit, exceed the limitations of a single solar panel's wires. But that's for another video, so let's continue where we left off before I went on that long tangent. Which was here, the battery being charged by the solar panel. And now we want to be able to draw current from the battery, use what we have saved up. It's okay to use a few wires with wire lugs attached to the terminals on the battery, just like we've done here with the solar charge controller, as well as that 60 amp fuse that will go to, I will show you in a bit. What we don't want to do is attach 4 or 5 extra wires from our different appliances to the battery studs, because 1, it looks messy, 2, connection won't be as good, it will be lug upon lug upon lug, which isn't the best thing to do really, because hotspots, not as good connection, as well as just an inconvenience having to remove every single lug if you want to get to the one at the bottom. So instead we can make a nice installation with something called a DC fuse block. These allow you to distribute your power to wherever you want it to go, as well as fuse it at the same time. As with everything, quality matters. If you get the cheapest, nastiest stuff for like €10 or £10 or dollars, you might end up with bad terminals, those screws you see where the plus and minus are. This one isn't the best, really, the one I got in the picture, because there's not a lot of surface area. You might think, oh, my fuse block says it's rated for 100 amps, but in actuality it's not. It's being limited by the terminals, the bolts, the nuts, because on these cheap ones you sometimes don't attach it directly to the actual bus bar. For some reason they've constructed it in such a way that the actual lug goes on top of the nuts, which then travel through the nuts and bolts to the bus bar. It's an inferior design, but never mind that, let's maybe talk about it later. Whoops, editing mistake, looks like we're going to talk about it now. The one of the picture here, specifically the one to the left, I'm not sure if you can see it, but where the plus and minus are, the top and bottom terminals, the actual metal surface area where you want the lug to be flush against, can't be accessed properly. The plastic goes up a bit. How it should be is the way they've done the other terminals, the smaller ones. If you look at those 6 top ones, the minus ones, those rectangular plates, the 2 ones, are what the actual wire lugs are supposed to be flush against, and then the screws or the bolts are only supposed to tighten down and keep the wires in place. But what they've done on this design on the main terminals is add an extra nut, and you're expected to attach your lug against the nut, of course with a washer in between. Still, that's not a lot of surface area, and that means that all the current is supposed to run through that nut, and a nut made of steel, no doubt. It's not the right way of doing things. You want something that looks a bit more like this. Sorry about the picture being a bit crappy, but anyway, you get the idea. You want to be able to contact or touch the metal directly, instead of just touching the bolt or the nut, because on this one, the plastic around is below the actual metal surface. One good brand I know of is Blue Sea Systems. Their fuse blocks are supposed to be great quality, and you can also tell by just how it's designed if you look at it or read reviews. They might be a little bit more pricey than the $10 ones or £10 ones, but you want to get something a bit more quality for this because it's kind of the brain of your system where the fuses go and it's all distributed. Also, it has a negative bus bar already on it. You see that top section? So with a small system, you're not going to have to buy an extra negative bus bar, so that saves money that way. There are also these. These are switches as well as fuses. Well, maybe not fuses, they are more like resettable fuses or circuit breakers. The upside is that you don't have to buy a new fuse and put it in there or replace them every single time. You can just simply press the button. Also, you don't have to buy separate switches for every single appliance because there are switches within the unit already. I've used these and they work fine, but I prefer the blade fuse block, the one I showed you earlier, because they are more likely to come with a negative bus bar. With these, you often have to buy a separate one. I mean, there might be those that have a negative slot as well, but I haven't seen one yet. But these are normally mounted so you can see them and access them all the time, while the fuse block and the bus bars and stuff are usually hidden behind walls or behind something anyway. I believe that fuse blocks might be a bit easier to understand, or at least visually see and understand for beginners, so I'll be using a fuse block in this video, but let me know in the comments if you want to know how to wire a switch panel as well. Now, there's that installed. As you can see, I've got 16 square millimeter wire as well as a 50 amp fuse. Yeah, I know it said 60 earlier, but you can use a 50 amp, a 60 amp, even a 70 amp. All of those fuses will protect a 16 millimeter squared wire. I'm just going to go ahead and use the 50 amp fuse because in this system I'm not going to be using too much current. It's never going to exceed 50. Also, I've actually gone ahead and used a cheap fuse block here, not the expensive, better quality ones, so I wouldn't want to push more than 50 amps through those terminals anyway. So you can't really use wire-to-wire here because the terminals aren't really big enough on many of these fuse blocks. You can size down though and use 10 square millimeter wire, but then you also have to size down the fuse to perhaps 40 amps. It all depends on how much you're going to use, how many appliances you're going to have. Speaking of appliances, let's add some. This fuse block is a 6-way fuse block. It means you can attach 6 different units to it. It's got 6 small terminals for the positive and 6 for the negative. Oh, and of course, the main positive and the main negative as well. There are many different types of fuse blocks, 4-way fuse blocks, 12-way ones, pick whichever you need. It might seem obvious, but I'm going to state it anyway. You don't have to add 6 appliances just because you've got a 6-way fuse block. For example, here, I'm just going to use 3 or maybe 4. Let's start with the fridge. As you can see, I've chosen to use 4mm squared wire. It may seem a little bit excessive, but let's walk through why we ought to use 4. So a lot of these 12-volt compressor fridges use about 60 watts when the compressor is running. Of course, the compressor turns itself on and off all the time when it reaches a certain temperature, either too warm or too cold. So when it's not running, it's going to be way less. The average wattage usually ends up being 45 watts, but that's just the average seen over time, then divided by hours. So, we can't really think that way when wiring the system. We have to think, what is the most this wire is going to carry? There is a simple equation. Watts divided by amps equals volts. And also, watts divided by volts equals amps. That means that volts times amps, or amps times volts, equals watts. So if our fridge can use about 60 watts when the compressor is running, then the equation follows 60 watts divided by 12 volts equals 5 amps. Now I know that the battery might be more than 12 volts really, like 12.8 or 13 or higher, but I'm going to use 12 volts in this equation because I'm lowballing it. I'd rather it say a little bit too many amps than too few. But divided by 12, divided by 12.8, it's going to be almost the same. Anyway, we're not done yet because the fridge actually uses more amps than 5. The compressor motor inside the fridge has a high inrush current, which means it uses more current when it first starts up. Not for long, it's just a split second where it kind of goes up, 2 to 3 times as high, maybe more sometimes, but we don't have to exaggerate and give ourselves 50 square millimeter wire because it's just for a split second, but we do want a little bit thicker wire. I'd say 5 amps times 3, which is 15 amps. So yeah, we could use a 2.5 square millimeter wire, but I would go higher. I've used 2.5 in the past, and Although the fridge did run, I did notice a voltage drop and it struggled, so I would go to 4. 4mm wire can handle 20 to 25 amps, no problem, within reasonable lengths that you might use inside a camper. This wire will mean a wider path for the current to travel, which is great. Less resistance, it keeps things cooler and keeps the voltage higher. Now let's just add the fuse at 15 amps, that way the wire is protected. We don't have to worry so much about the fuse blowing because of the surge current or inrush current being perhaps 15 amps, because it's just for a split second, so it won't really blow. Should you be unfortunate enough and have it blow anyway, because maybe your fridge's inrush current is even higher, then you can always change the 15 amp fuse for a 20 amp fuse, because 20 amps is still suitable for a 4mm wire. Now on to the next appliance, the roof fan. Here I've used 1.5 square millimeter wire and a 5 amp fuse. This is because a lot of 12 volt roof fans use about 30 watts. So let's take it through that same equation. 30 watts divided by 12 volts equals 2.5 amps. So for this I would absolutely use 1.5 square millimeter wire because it can handle it no problem. You can add another fan in the future and it would still handle it no problem. 1.5mm wire is cheap, so I just get that and not bother buying extra packets of smaller wire. Now let's talk about the lights, because this is not good enough. First of all, unless you enjoy living in dark caves, one light is not sufficient enough if we're talking about 12 volt spotlights. So let's make that 6. These spotlights often come with wires attached to them, like this, one positive and one negative. The way we want to wire it is in parallel, which means all the positives connect together, and all the negatives connect together, and then back to the fuse block. By the way, let me know if you want another video showing how to actually crimp and connect things in real life. When you wire your lights in parallel like this, all your lights get the same voltage supply, in this case 12 volts, or more like 12.5 to 13.5 in reality, but never mind that. As for the current, the total current will be all of the individual lights' currents added together. If each light draws 0.2 amps, this is of course LED lights, not any other type, then the total current will be 6 lights times 0.2 amps equals 1.2 amps in total. This is how you'll wire 99% of the times in an RV for just normal roof lights. Do not do it this way. This is wired in series, meaning the voltage will get divided. If all of your lights are the same, which they probably will be if you order them in a pack, then internally the resistance as well as the forward voltage, which is not the same as voltage, in every light will be the same as well. Because they're the same, the voltage will simply divide equally between them. Take 12 volts divided by 6 lights and you get 2 volts per light. It's not enough to light them up. If you instead have 6 different lights with all sorts of resistances, some lights may glow a little bit, others may not glow at all, some will be bright, depending on the resistance inside them. So, wiring them in series is not correct here. Wire them instead in parallel, like I showed you first. You might also want to add a switch, unless you want your lights to shine constantly, but that's a waste of power. Some lights can come with switches internally, where you kind of just press the glass or the light area and it switches on or off. I'm not a big fan of them, and I've heard that they can kind of give up before the light does, and it's probably easier and cheaper to change a little switch than to change the whole light, unless you know how to fix the light and the internal switch. But that's just me. I prefer the smaller switches. Though you don't have to get necessarily the small switch I've got in the photo here. There are these. These are like switchboards, if you want all your switches to be in the same place. This particular switchboard doesn't appear to have any fuses built in or anything like that. It's merely the switch panel, not the fuse switch panel I showed you earlier. I will admit, I think that these switch panels look sort of cool and a bit professional maybe, but I'm not sure I'd want to use one myself because, for example, if you're in bed and you want to switch off your night light, it would be a bit easier. I mean, it's a bit lazy, I know, but it would be a bit easier to have the switch by the bed. And you might want to have your water pump switch by the kitchen tap. This way you don't have to run over to the switch panel every single time you want to use an appliance. Feel free to pause and read if you like, but you don't have to. What I'm trying to do here is just explain how to calculate what fuse you need for the load and what wire to use. Start by looking at your appliance and how many amps it will draw during normal operation. Then times that by 1.25. That will give you a 25% higher rating than the actual load. So let's say you have an electrical heater and it draws 10 amps. 10 times 1.25 is 12.5. Though a lot of fuses come in standard sizes, like blade fuses. Here the closest one to 12.5, thinking upwards, would be the 15 amp fuse. Here I would use a 2.5 square millimeter wire. It can easily handle 10 amps, which is what the heater will be drawing, and then the fuse can easily handle the 10 amps and will only blow during a short circuit. Or if you should try to pull 15 or more amps, and the 2.5 square millimeter wire can handle more than 15 amps, which is the limit of the fuse. So this means that the fuse will blow before the wire burns. Technically, you could use a 1.5 square millimeter wire for a 10 amp load such as the heater. The problem is that we still need to fuse the wire, and we can't use a 10 amp fuse here because the load, or the heater, uses 10 amps, so it will make the fuse blow. So we have to use the next size up, which in the case of blade fuses means a 15 amp fuse. But the 15 amp fuse can typically handle more current than a 1.5 square millimeter wire. At least when the wires start getting a little bit longer than just short stumps. And we don't want to risk the wire being the weaker link. So therefore, we'd use a 2.5 square millimeter wire with a 15 amp fuse here. Now, this picture is not necessarily written in stone. It all depends on how you install this stuff and also how long the wires are, but it's a bit of a guideline if you like. There are others online if you'd prefer to look at those, but this is sometimes how I think. Okay, now if you remember in the beginning I said I'd show you an alternative way of wiring things if you don't want to use extra bus bars, and to simply use what you already have in this installation. I would not use this method if I had a large solar array with many panels and a lot of current running through the wires and even high volts. But for a small solar system like this, it should work just fine. So if you want it to look a little bit cleaner and not have everything go to the battery terminals, you can wire it to the fuse block. I know that most people only use these to draw current from appliances, but there is no reason why you can't use a fuse block to charge as well, as long as it's a good quality one and you don't exceed the ratings. Internally, it's just a positive bus bar with slots for fuses, as well as a negative bus bar, plus all the terminals. Let's open one up and I'll show you what I mean. This is a budget version, but the more expensive ones work on the same principle, so let's open it up. By the way, in case it wasn't obvious, you do not have to open up these like this to wire things. This is just to demonstrate something. So, see that bottom bolt there? That's the positive terminal, or the other side of it, where you normally put the lug. So I know I said earlier electron flow is negative to positive, but just to make things simple and easy to understand, I'm just going to go ahead and say, when you use appliances, current will flow from the battery through the wire to the stud, and then of course that's connected to this spine-looking bus bar, and all these small teeth, or whatever you want to call them, that are connected to this bus bar, you can actually just go ahead and ignore those red wires as well as that little tiny black wire at the top, because they are just for the LED lights, but never mind that. So anyway, once the current's flown through the wire to the stud and reached the main bus bar with all of these small teeth, it does not get any further. There's a small gap, as you can see, between the teeth that are attached to the actual bus bar and the teeth attached to all these 12 small mini studs for each appliance. So when you need current to flow to the other side in order for it to reach your appliance, you build a bridge by adding a blade fuse. So it flows from the pin over there and to the other pin. Now to my left there, you see that little negative part of the fuse block I've taken apart. After the current has been through the appliance and made it run, it then goes through the minus wire of the appliance, back to this negative bus bar via one of the smaller studs or screw terminals, and then to the main stud or wire that goes back to the battery. So when we wire the solar charge controller to the fuse block, say we use the top left terminal for the positive wire, current will flow when the sun is shining to that terminal, through the fuse, and onto the main spine-looking bus bar. Keep in mind, the bus bar is basically just an extension of the actual battery stud or terminal. Current will still flow where it needs to go. For example, if we've got an appliance that needs 10 amps to work, and the solar charge controller can only produce, 7 amps, then 7 amps will flow from the solar charge controller to that terminal and then to the bus bar and where it needs to go directly, without going to the battery first. And the remaining 3 amps will come from the battery. If instead we have an appliance that only draws 7 amps and the solar charge controller can produce 7 amps at that given time, then it will go straight, the current that is, will go straight to the appliance from the solar charge controller. No current will be drawn from the battery, but also the battery won't be getting charged. Final example. Let's say that the appliance only needs 5 amps, the solar charge controller can produce 7 for example. What happens here is the remaining 2 amps will go to the battery and charge it, or to another appliance if you've got one of those on running at the same time. My point is everything will run through the bus bar because the bus bar is just an extension of the positive terminal and the negative terminal. So it's not like current will be flowing both through the wire that goes into the battery and away from it at the same time, causing current to crash into each other. That's not how it works. It goes to where it's needed. Now you don't have to have this, but I'd probably add a battery switch or battery isolator. It goes on the 16 square millimeter wire. This way you can shut the power off from the battery to the fuse block. It's in case you ever want to do a bit of work or simply just want to switch the power off for whatever reason. Fuse placement is pretty obvious here. It just goes where the rest of the blade fuses go, up there. As things are now, if there should be a short between the BAT terminal wires between the MPPT solar charge controller and the fuse block, then the 15 to 20 amp fuse will protect these wires. Should instead a short circuit happen between the two 16 square millimeter wires, then the 50 amp fuse will protect them. Now back to the blade fuse. The 15 amp fuse works fine here because it's still weaker than the wire, but at the same time can handle the current that will flow normally when it charges. But you can also upgrade it to a 20 amp fuse because you might want to get more solar panels in the future, and both the 4 and 6 square millimeter wire can handle that sort of current, so it's future proofed if you get a 20 amp fuse and it's fine. I know this is a small system, but I'll say it again anyway. If you want anything bigger, get a good fuse block, like Blue Sea Systems or something similar. I'm not sponsored, but these cheaper fuse blocks might say 100 amps total and 30 amps per terminal, like the small terminals. Don't trust that. I would not want to go over 15 to 20 amps per small terminal and over 50 amps for the whole thing. If you're still watching, I'd like to add in a few last tips. Make sure to pull them in groups, that is to say, the positive and the negative going from the fuse block and to an appliance, try to put them together, because should, for example, anything short between them, the fuse will protect those two wires. But it's not completely foolproof. For example, if you were to run those thin wires not paired together, you might have them go all spaghetti junction-y, and one of the small, thin, black wires of anything really, but in this case the MPPT solar charge controller, should that thin black wire get in contact with the thick positive wire, the 16mm one connected to that 50 amp fuse, then we risk that thin black wire becoming the new fuse, because it might not be able to carry as much as that 50 amp fuse, and definitely not be able to carry more than the 16mm wire. So there is a fire risk involved there. To avoid this, or at least minimise the risks, have a neat looking system where you have those two thin wires run together away from the battery terminals or other thick wires that they might potentially get squashed against. Also build your system in a way that the risk or the chances of them getting squashed doesn't happen in the first place. Don't have any sharp edges close to those wires. Now, by having these thinner wires, or any pair of wires, a positive and a negative, running to an appliance or anything, by having the pair next to each other all the time, should for some weird reason the thick wire, like the 16mm wire here, get damaged or pinched and also squash at the same time and touch the thinner wires, there is a greater chance that you'll squish both of the thin wires, meaning there'll be a short between the both thin wires as well. So then the smaller 15 to 20 amp fuse in this case would blow and protect the small wires. Now, two last pieces of advice. Tighten everything properly, all the terminals, and also make sure that they are tight a few weeks or months after, every now and then. It can help avoid hot spots or like burnt terminals and fires and stuff. Or just you losing your power. Best case scenario. Final words? Don't use the load terminals on the MPPT solar charge controller if you can help it. They're not the best. They are used for very, very small loads, maybe lights if you like, and it's more convenient to wire it that way. But don't make it a habit. It's more prudent to use a bus bar go directly to the battery. One less connection. If you have any questions about this particular diagram or any other questions about installation in general and want to see other diagrams, let me know down below in the comments. Thanks for watching.